All right, welcome everyone. Today we are talking about theory-based hypothesis tests. So can someone remind us what a p-value is? Sam?
The probability of getting a value of the statistic at least as extreme as the observed.
Yeah, the p-value is the probability of getting a value of the statistic at least as extreme as what we observed in the data, assuming what?
The chance model is correct.
Yeah, assuming the chance model or the null hypothesis is correct. So because the p-value is a probability, we have two sort of big overarching options for how we compute it. One way is the way we talked about last time, which is to simulate data according to the null hypothesis. And for that simulated data, we can compute our statistic. We do this many times, so we get a distribution of the possible values of that statistic. So that gives us what we can call an empirical p-value. Empirical because it's based on evidence from simulations. And this approach is really good if you don't know the distribution of the test statistic. If the statistic you're investigating is something weird, like maybe 3 times the median minus the mean, where it doesn't have a nice distribution that is one of the ones that we know from Math 346. Option 2 is to use probability theory to compute the probability. So if we do this, then we need a model for the distribution of the statistic. And just like in option 1, we want that model to be based on assuming that the null hypothesis is true, because that's what we're always assuming or conditioning on when we're computing a p-value. So let's think about what this looks like in the context of a problem. Read through the introduction to problem 1, and then try parts A through C. So for folks watching online, this is the test of a proportion and mean activity that's right here. All right. So what should I put for my null hypothesis here? Sam, you want to give it a go? That sounds good. We want our null hypothesis to provide us with a specific model for the chance model of what happens if any difference from 20% is just due to randomness in who we sample. So that would say that the true proportion of patients who experience side effects is 0.2. So P is the true proportion of all patients who use this medication who experience side effects. So we're making it clear that we're not just talking about the sample here, we're talking about the population of all the patients who use this medication. And then what should I use for my alternative hypothesis? Maria? Yeah, because that's what the company would like to claim. They want to be able to claim that fewer than 20% experience side effects. So they're only interested in a one-sided alternative hypothesis. Because we have this P is less than or equal to 0.2 in the alternative hypothesis, it would also be fine to write your null hypothesis as P is greater than or equal to 0.2. Whichever way you write your null hypothesis isn't really going to make a difference in how we compute the p-value, because we're always taking the one model that's specified by the equal sign in this null hypothesis. All right, so if we use our test statistic as the number of patients in the sample who experience side effects, what probability distribution would we want to use to model that? Sam?
I said that.
Yeah, sounds good. We have the number of successes or number of yeses in a yes-no outcome with a fixed number of trials. So a binomial distribution is probably going to be a good way to go. What are the parameters for that binomial distribution? Maria? 400.2. Yeah, so N is 400 and P is 0.2. So that's where we're using our null hypothesis. The 56 is going to be an argument for the binomial CDF when you compute the probability. It's not really a parameter for the distribution because it doesn't control the shape of the distribution. All right, so then if we want to use a binomial distribution, what assumption do we need to make about the y sub i's, or about y perhaps? Isaac?
They're approximately normal.
No, if we want to use a normal distribution, then we'd need to be able to assume that it's approximately normal. Joey? Yeah, we need to be able to assume that the responses of each of the patients in the sample are independent. So this is very common when we're computing probability theory-based p-values, is that most models that we would use to compute a p-value assume independent observations. Can anybody think of an example when this wouldn't be true? That is where the assumption of independence would be a bad assumption. So there are sort of two main situations when you can't assume independence of your responses. One of them is if you're taking a convenience sample. So this is where you're taking a sample like without really thinking about it, or without generating random numbers. So maybe you're just going to survey your friends, or you're gonna walk around a street and survey people that you bump into that happen to be willing to answer your survey. So a sample that's convenient for you to take, might be very easy to gather that data, but that leaves open the possibility for human bias to influence the results. So when you take a convenience sample, you might be either consciously or unconsciously thinking something like, oh, the last person I surveyed was a senior citizen. It'd be really nice to make sure I get a college student in my sample. So in some sense that makes sense, like you want to get a diverse sample, but that means that now any results from your survey that are associated with age are now not independent. So a better approach to taking a sample is simple random sampling. So this is when you take a sample such that every sample of size n, whatever sample size you chose, is equally likely to happen. So the most common way to do this is to assign a number to every member of the population. So for example, you might start with a directory of all UWEC students and just number them off. 1, 2, 3, 4, ... up to 10,432 or however many there are. And then use a random number generator to generate n numbers from that list. And then those n people are the ones you would survey. So simple random sampling isn't the only way to get a good sample. Like it's not the only option besides convenient sampling. But simple random sampling is sort of the most straightforward, good sampling method that you can use. And it results in all of your observations being independent. So we're typically going to assume simple random sampling when we're doing hypothesis testing in this class, because it lets us use the binomial distribution or the normal distribution. It lets us use these models that are based on independence. Questions about this? All right. There's one other major situation where independence of your observations can fail. Imagine for a moment that you have a population of 52 cards, playing cards, and you want to sample 5 different cards to test if the proportion of cards that are hearts is different from 1/4. Why are the observations in your sample not independent in this case? Sam?
Because like once you draw one heart, the percentage of getting another one goes down.
Yeah, your probability that the next card is a heart depends on how many hearts you've taken out of the deck so far. So if you were computing a probability involving this scenario, you'd end up drawing a conditional probability tree like we did back in Math 346. So in general, make this smaller so it's not this much here, right? When your sample size n is greater than 5% of the population size, independence isn't a good model when you're sampling without replacement. That is, when you're doing your sampling and not putting people back into the population after you sample them. So like you're making sure that you're not surveying the same person twice. Independence is not a good model if your sample size is large compared to your population size. But this doesn't mean that you should artificially reduce your sample size in order to get your sample size to be less than 5% of the population. Having a large sample is still good. It still gives you more information. But in that case, instead of using a binomial distribution here, we would need to use a hypergeometric distribution. And if this is interesting to you, this idea of how do we deal with the fact that our population size is finite, and what happens if we're not taking a simple random sample, if we're doing some other kind of sample instead, I recommend taking Math 445, survey sampling. All right. So for our problem about testing for side effects of this medication, let's go ahead and suppose that the company took a simple random sample and they were studying a large population, so that 400 is less than 5% of the population. Go ahead and use a binomial distribution to compute the p-value. All right. So our p-value is going to be the probability of a test statistic that's at least as extreme as what we observed in the data. And what counts as at least as extreme is going to depend on the direction of our alternative hypothesis. So in our data, 14% of patients had side effects. So that's evidence that the proportion who experience side effects is less than 20%. So what counts as more extreme evidence or more convincing evidence would be if 13% of patients experience side effects or 10% of patients experience side effects. So if Y was less than 56, that would be more convincing evidence against the null hypothesis and in favor of the alternative hypothesis. So for our p-value, we want to find the probability that Y is less than or equal to 56. And we can do that using a binomial distribution, using binom CDF of 400, 0.2. So that's using the parameters that we used from part B. That's using our assumption of supposing we're in the world where the null hypothesis is true. And because we're finding the probability that Y is less than or equal to 56, we don't need to do any funny business with subtracting 1. We can just put in 56 directly. Questions about this? All right, so an alternative model for the distribution for Y uses an idea back from chapter 7, where we said that if our sample size n is greater than 9 times the maximum of P and Q divided by the minimum of P and Q, then we can use the normal distribution as an approximation to the binomial distribution. So here, we're using our value of P from the null hypothesis, which was 0.2. So Q is 0.8. So the maximum of those is 0.8 and the minimum is 0.2. So we have 9 times 0.8 over 0.2, which is 36. And our sample size N was 400. So that means we could also use a normal approximation for Y as a way to get an approximate p-value. That's often a little bit easier than using binomial CDF. If your alternative hypothesis is two-sided, that means you don't have to calculate two probabilities and then add them together. So to compute the probability that Y is less than or equal to 56 using a normal distribution, we could use normal CDF, but your calculator has a built-in function for this by going to stat and then tests and then the one prop z test, which stands for one proportion z test. And the z in here is referring to the fact that this is using a standard normal distribution. So like a z-score. So go ahead and try computing the p-value for this problem using a normal approximation. So in other words, using the one proportion z-test. So in the output, it's going to give you z. That's the standardized statistic, or in other words, the z-score that corresponds to your data value of 56. The thing that's labeled as p is the p-value, and the thing that's labeled as p hat is the sample proportion. So that's just 56 divided by 400. So you should find here that your p-value is pretty close to the p-value we got using the binomial distribution, because we said that the normal approximation should be a good model for the binomial distribution here. But it's not going to be spot on because this is just an approximation. Does that agree with what people found? All right. Any questions about this? All right. So let's turn our attention now to a problem involving testing means rather than proportions. So read the setup for problem 2 and then try problem A. You need to be able to explain to your clients that you're not just talking about the sample. All right. So because we're talking about a mean here, I would probably use the symbol mu to represent our parameter. So our null hypothesis can be that mu equals 25.4 minutes per day. Where mu, what does mu represent here? Kyle.
The average commute time.
The average commute time among whom?
Well, the null hypothesis would be among everyone.
Everyone in the US?
Yeah.
So we originally got this 25.4 minutes per day figure from everyone in the US. But the sample was taken from Wisconsinites who work at least 20 hours per week. So when we're thinking about generalizing from our sample to a larger population, that's the population that we're interested in. That our goal here is to test whether Wisconsin is different from the rest of the US or from the whole US. So mu should be the average commute time among all Wisconsinites who work at least 20 hours per week. Are there questions about that? So we're taking the 25.4 as being a given for all Americans who have jobs. We're taking that as a fact. And the thing we want to investigate is whether that's also true for Wisconsinites. All right. So for my alternative hypothesis, we're going to use the same parameter symbol and the same value to compare to as the null hypothesis. So we still have mu, we still have 25.4. What inequality should I use in between those two? Not equal to, yeah. So the Wisconsin DOT wanted to test whether the average was different in Wisconsin. And they didn't have a prior idea of we expect it to be less in Wisconsin or we expect it to be more. So because of that, we're interested in differences on either side of 25.4. So we're going to test whether mu is not equal to 25.4. And an important point here is that we pick this direction of inequality based on sort of what the research question is before we look at what the data was. So the fact that the data said 24.4 minutes, the fact that that's less than 25.4, that doesn't play a role. Questions about this? All right, so let's talk about what we might want to use as a test statistic and a model. So we need a test statistic that's going to depend on the data, the y sub i's. And we need to know what its distribution is, assuming that the null hypothesis is true. So one possibility would be if we knew the population standard deviation sigma, then we could just say that y bar was approximately normal with a mean of mu naught, so the value from the null hypothesis, and a standard deviation of sigma over the square root of n. Or equivalently, we could use y bar minus mu naught divided by sigma over the square root of n. And we could say that that had a normal distribution with mean 0 and standard deviation 1. So if you're in this situation where you know sigma, that's known as a z-test, which your calculator can do for you. But in this problem, we don't know the population standard deviation sigma. We only know the standard deviation from this sample. So any guesses about what we might use for a test statistic in this case? That's going to be the test. So what's the test statistic going to be? How might we modify this y bar minus mu naught over sigma over the square root of n if we don't know sigma? Sam? Yeah, if we replace that with the sample standard deviation S, what's that going to do to the distribution? Very good. These things keep coming back. So our test statistic will be y bar minus mu naught over S over the square root of n. And that's going to have a t distribution with n minus 1 degrees of freedom. So to do this on your calculator, you can go to stat and then tests and then t-test. And generally, you're going to use input equal to stats. If you had the raw data and you wanted to type that into list L1 on your calculator, then you could use input data instead. So go ahead and try computing the p-value for this study, and then write your conclusion based on that p-value. So there is or there isn't enough evidence to claim alternative methods. All right, so what'd you get for a p-value here? .58. All right, so that's greater than 0.05. So we're going to fail to reject the null hypothesis. Or in other words, we'll retain the null hypothesis. Meaning, we're not going to accept it. We're not going to claim that the average in Wisconsin is definitely exactly the same as the rest of the US. But we're going to keep the null hypothesis as around as something that we think is plausible. So it's plausible that the average commute time in Wisconsin is 25.4 minutes. It's also plausible that it's not 25.4 minutes, but it might be something close to that. It might be 25.6 minutes, might be 25.1 minutes, somewhere around there. So the way we put that in the context of the study would be to say there is not enough evidence to claim that, and then fill in the blank with the alternative hypothesis. So there's not enough evidence to claim that the average commute time in Wisconsin is different from 25.4 minutes per day, or is different from the average in the whole US. Or we could say it is plausible or believable that the average commute time in Wisconsin is 25.4 minutes per day. Got it.
What would P have to equal to where it wouldn't be possible? Would it have to be less than 0.05?
Right, so whatever our significance level is, if the p-value is less than or equal to that, then we would be rejecting the null hypothesis and claiming that the null hypothesis is not plausible, so there is enough evidence to claim the alternative hypothesis. Questions about this? All right, great job today. I will see you in lab tomorrow for using R to investigate hypothesis tests.